笑眯眯，都笑眯眯。OK，刚考完，哦，刚考完了。
order of element, which in there. 你在耍？是有，那个英语，我是做那个搞到我在放。这应该是，我不确定了。那可以，是吧？这个我们去这个上这个东西我行，说。这上次是本来就Hello. Hello. 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 Okay. Okay. So let's start new lecture for today. We will continue with compactness.
continue with compactness. I think we will continue compactness up to compactness in metric space. And since we already reached compactness in metric space, then I think we will do completeness first. Okay, and then we will do completeness. And then after completeness should be the Ascoli, what's the name? You guys encounter a theorem called Ascola theorem? Not yet? Not yet. Okay. For that part, we will move to the end of the semester, because to prove that theorem, to prove the generalization of Ascoli theorem, we need infinite product space is compact, and that one will require some other tools in topology. So we will introduce other property of topology, namely how many number of basis element is enough to generate your topology. Okay, yeah, and that will be done after completeness in metric space or in general topological space. Okay, so we will continue with compactness. All right, so first proposition we have is a topological space is compact if and only if every open cover of X by basis elements has a finite subcover. Okay, so looking at this statement, right, which direction is obvious? Which direction is obvious? Left to right or right to left? Left to right. Why? Continue. Huraikan, so your answer. Elaborate more. What's the definition of compactness? So how do you have this left to right implication? This is fast. No, you should start from the definition, right? Definition says every open cover has a finite subcover.
Because this the definition.
Okay, so you need to discern the sentence that we have, right? Compactness. So let me write down the compactness definition. By definition of compactness of X, every open cover of X has a finite subcover. So what's the difference here? What's the difference between these two statements? Okay. Hey, don't throw me, just throw me word like that. This one is like kindergarten, you know. You need to give me a functional sentence, right? Okay. So what basis? So what's the difference between these two lines? The two statements then. So in the theorem, the open cover is covered by what? basis elements. The definition of compactness is covered by what? Any open set. Right. So basis element is also a open set. So since every open cover has a finite subcover, in particular, open cover by basis element is also an open cover. So it has a finite subcover. Does it make sense? Do you get what I say? Don't get is okay. Can keep asking. So what's the difference between these two statements? Let me ask you. What's the difference? What's the difference? Hey, difference very quick one, right? By basis element, just these three words. No need to think so long one. Right? So by basis element, this one is open cover. What does this mean? Open cover what? What's the thing inside open cover here? Any open set. 任意的 open set。basis element 是不是其中一个 open set？ 对不对 ？Okay, so if you have this statement here, then you can apply this statement to the specific open set, which is the basis element. OK 啊，一定要明白啊，因为没有什么特别的人 ，OK， 一定要明白这个。So there's nothing weird here. So we will say the left to right is obvious because open cover by a basis element is one of the case of open cover. Okay. So the other case is not quite obvious, but almost immediate. Okay, almost immediate. So should I let you think about it? So discuss with your friend. I'll give you 3 minutes. Discuss with your friend how to prove the other direction. Okay, discuss with your friend how to prove the other direction. If you just only know that the cover by a basis element has finite subcover, how can you talk about any open subcover? I mean open cover that has a finite subcover. How can you generalize from basis element? Sorry? Mm-hmm. Every open set is the union of basis element, sure. So how do you start? How do you start? How do you start? Suppose C is an open cover of X, and then you want to show that C has a finite subcover. Okay, and then what do you do? Okay, every element C in C can be written as union of Bi in B, where B is a basis of the topology. Okay, and then all right, so since what? Since union of C in C of C is equals to the union of some Bi in B, and then you sum all of them, right? So maybe we want to remember the C, right? So let's put the C here. Put the C here. Perhaps. And then since if you take all the C that cover your space, and then for each C, you write it as a union of basis element. So the whole thing here is a cover, is an open. So since this is equal, then it is an open cover of X by basis element. Okay, good. So what's next? So we can reduce the number in the union of BIC then, right? So there's this assumption. There's this finite collection of BIC such that what? Such that union of let's say how should we put this? Let's say BIC. Maybe we label it with J equals to 1. That cover who? Cover X. Okay, but you only reduce the number of basis element, right? But how do you pick the C? How do you pick up the finite number of C that cover it? Huh? So you simply pick Ci such that Bi is in Ci. Okay, so we simply choose. How do we choose this? So we choose Cj such that X is in the let's say BIC1 union of 2 BIC n, and then this whole thing is in CIC1 up to CIC. Okay, does it make sense? Any question or not? Question? Just ask. Feel free to ask. Question? Ah? Oh, right. So there's some issue here. So maybe let's just to like this C1 up to Cj. Sorry, Cn. So J is going from like 1 to. Okay.
Cj is a subset of B.
Which direction? So I think we want such that so be more specific a bit. So such that Cj contains Bj like this. Like this. Okay, yeah. Good. Then we will get this. Okay, clear? Is it clear? Okay. Okay. So yeah. All right. So why we want to do this? Because we want to reduce checking compactness to just checking open cover by basis element. If you have control on the basis of topology, okay, you don't need to consider random open cover. You just consider open cover by basis element. In particular, this is useful when we want to show for uh, finite Cartesian product space of compact space is compact. Okay, so if x1, x2, to xn compact, then x1 cross x2 cross until Sn is also compact. Okay. So we will just prove the case when n equals to 2. And then for finite n, you just proceed by induction. Okay. Yeah. So let's just prove let's just prove that S cross Y is compact if X, Y are compact. Okay. Then the finite case will follow by induction. Okay, so if you don't know how this follows by induction, right, I suggest you to write it out. Okay, please write it out. Okay, then you will understand every time what people say, oh, by induction, by induction, by induction. Okay, it's really just a routine by induction step. Let's try and work it out if you don't know. If you don't know, practice it. Okay, so how to prove? How to prove the product set is compact? Knowing that individual space is compact. Any idea? So you know that along each space, right, every open cover has a finite subcover. Okay, for example, a prototype for S cross Y is what? R cross R, right? So it's R2. Okay, R2. Sorry, R is not compact, right? Okay, so let's pick some compact subset of R. Maybe -1 to 1 cross interval. Okay, and then you cross two of them. What do you get? You get a grid, right? So what's grid is that? Huh? Yeah, it's a square. So what square is that? What's the vertexes? -1, -1, -1, 1, 1, 1, and 1 -1. Right. So that grid. Why is that compact? If you know that -1, 1 is compact. Huh? Why? Yeah, that's the idea. So how do you write it out? That's the idea. So I mean, we can try and cover a line first. Yeah, we can try and cover a line first. So we can try and cover a line first. So for uh for given x, so given 1 point here. Okay, what can we consider? We can consider the space singleton x crossways y. I just look at one line. Okay, what is this space? This space is actually homeomorphic to y. What does this homeomorphism do? I just forget x. I just forget x. Is a bijection, right? Identity should be continuous, right? Identity map. Okay, because I didn't change any topology between these two y. Okay, topology is the same. So since y is compact, what can I do? Homeomorphism also sends compact space to compact space. So since y is compact, singleton cross y is also compact. Is also compact. So what does this mean? So let's draw some picture, right? So let's draw some picture. X and let's say y. This. So let's say this point is the little x. So here this line is little x cross y. So this space is compact. What does it mean? If I have a open cover around this space, it has a finite subcover. So what does the open set here look like? What does the open set here look like? What does the open set here look like? Hmm? Right. So some open set in X cross with some open set in Y. But how we define the product topology? How we define it? How do we define it? Sorry? How we define it? Finite entry is open. Sorry? You want to finish first? Huh? 之前 to finish? What do you say? Open set, cross open set is open. Actually, that's the box topology, right? Yes. So for finite case, box topology and product topology is the same. But it's easier to think about box topology. Because if we talk about product topology, right? Remember how we define it? Quite troublesome. We need to use the projection map and then pull it back and then generate as a sub-basis. So you need to consider finite intersection. But box topology, very easy. I throw in all the product of open set as my basis. Okay, since they are equivalent, we just use box topology to talk about this product topology. Okay, so it's better, again, better to describe our basis. So, so how should we write this? So how should we write this? So how should we write this? If we start with an open set here, not here. Okay, so how do we start this? So how should we start? So suppose C is an open cover of X cross Y. Okay, and then what do you want to show? So not just open cover, we just consider open cover by basis elements. Because from the previous theorem, we know that we can reduce just to checking open cover by basis elements. And this is how we describe our product topology or box topology. Okay. So suppose C is an open cover by basis element of XY. What do we want to show? We want to show that there exists a finite sub collection of C which also covers S cross Y. Okay, so this is what we want to do. So this is what we want to do. So how does this covering one line helps us to do this? Any idea? So I mean, so C cover the whole space, right? In particular, C also cover that particular line. Then, since that line is compact, then what? Then there exists a finite subcover. Let's call it CX from C that covers the line X cross Y. Does it make sense? Okay. Okay. Then what can we do next? So for every line, you can do this. There's a finite subcover for every line. Okay. But, sorry? Yeah, you can unit everything. But let's say your space is like infinitely many, you still infinitely many. Infinitely many of finite things still infinite, right? Okay. So what to do next? So you need to settle the horizontal part. Do the same thing to the horizontal, right? Okay. What can you do the same thing to the horizontal? How can you do it? What can you do to the horizontal one? Sure. You combine the two things together. Intersection? Second. Sure. Okay. So I mean, for each line, you can find finite cover. And then for horizontal line, you also can find finite cover. But how do you argue that union of all the finite cover can cover the whole thing? Right. How can you be sure you didn't miss out anything? Hmm? Sorry. Yes. E- I mean, you are talking about this. All the x cross y, I mean like this. Okay. Then I will it cover. Of course, the point you take will cover, right? But the how the open set will cover. How do you prove that? I mean, maybe obviously like there will be overlap, but how do you argue? Right? So on the vertical line, you can cover with finite subcover. With the horizontal line, you also can cover with a finite subcover. So the problem now is how you argue that if you put all these things together, you won't miss any point. Hmm? Try and think about that. Okay, while you are thinking, let's go a little bit more detail. How to look at this CX? How does CX look like? There are finite things there, but how does it look like? So we can write CX to be U1 cross V1, say, U2 cross V2, and so on, up to UN cross Vn for finite. Okay, this thing is in C, and moreover, it covers the line, what? The singleton cross Y. Okay, how can you think about this product of open set here? How can you think about it? Really, maybe you can think about it like this. Maybe I think maybe square is better. Let's do square. Have it like this. Okay. like that, and so on. Okay, makes sense? Makes sense, right? Okay. Then, what can you do? You want to take union? You mean union the CX take the cover, right? New cover, right? But you see, if you take union, the sum hole here. I know. How do you sure that maybe there's one X here? I can I can make some, how's that, non-overlapping open set. You get what I mean? You sure you can meet you can you can never miss by doing that? I'm not sure. I'm not sure. But at least this is not written in the text. I think you can do some tricky stuff that can miss some point. You can try and write it out actually, because I never tried that argument before. You can try with a union. But what we can do is we just take the intersection. So we just clean up the part they don't intersect. You get what I mean? Because there are only finitely many of them, right? If I just intersect all the open set, still open. Right or not? Okay, but by doing this, we will have a like uniform covering for the line. Yes. Yes. Yes.
And then at the middle part of the square, you don't intersect with anything, right? And then it's
Everything.
because you like intersect here, you say intersection. Or what intersect you take actually?
Oh yeah. So what intersection we take actually? So let's see. So what intersection we take actually? So at first I was thinking like maybe we can do like this. We're taking union or intersection here. Let me see. Union or intersection? Should be union, huh? Yeah, should be union. Because at first I thought I was like doing this thing. Yeah. But seems like sometimes you will miss out, right? Like what you say. Correct. Yeah. Okay, I think you're right.
For each.
At least not for this line. No? At least not for this line. Yeah. Yeah. Most probably. Yeah. Okay, I think you're right. Yeah.
Larger bit, so this cover a little bit, something like that. Yes, right.
Okay, let's continue first. Let's see how it goes. Okay, let's see how it goes. So what can we do here? So what can we do? So you want to form the union, is it? So let's form the union. So I mean, wait, let me see. Wait, so what kind of union you are forming? Let us write down first. Write down what's the union you want to try for. So you want to take UX cross VX to be the union of I from 1 to n of UI. Is it? This is what you say? Is this what you say? This is what you guys say, right? I take the union of everything. And this is the open cover for. This is the whole open cover for that line. Okay. But what am I thinking about is I didn't take intersection about this set here. So I want to focus on this line. So how do I focus on this line? So instead, I taking intersection between these open set. Okay. I just take the intersection between these UI. You get what I say? If I take intersection of this UI, what happens? I really pick out this the part that how to say, I cannot say they overlap, right? Because after I take this intersection, right, I need to cross with the usual VI. Also cover. Okay, so let's put here, this is the first construction here. Maybe I try my construction. So let UX be U1 intercept and from where to where for all the UI. Then what we can see is US cross VI is a subset of U I cross VI. Okay. I trim it. In that case, it's like I trim the band. Okay, let's say if we call this cover a band, we string the band. Okay. Okay. We string it. We trim it. Trim this extra part here. Fair enough. Okay. And then what? Okay. Okay, we got two method here. So let's go together. So let's discover possibility, right? So because what yeah. So let's explore possibilities. Okay. Let's do these two cases here. Okay. So our next approach is the same. Do it for every X. Our next approach is the same. Okay, do it for every X. So let's do my approach first. Okay, let's do my approach first. So from 2, let's do my approach first. So next approach is also the same. So what we do is we consider the open cover UX. Hey, please follow this part. Please follow this part. I know that this is a bit impromptu, but this is the exact impromptu that I want you to practice at your home. Okay, this is the exact impromptu you need to practice at your home. It's like you do my assignment, right? You don't know how to do, and then you try some ideas. So now I'm trying your ideas. Let's see how I treat your ideas. I know you spend a lot of time running into wrong ideas, right, when you do assignments. So now you put your idea to me, see how I deal with your ideas. Okay, learn how I deal with your ideas. Okay, so now do my idea first. Okay, then I will do your ideas. Okay, please learn this. This is an important skill to do your assignment. Okay, so that you won't spend too many unnecessary time. Okay, so consider that the open cover UX. Can or not? This sentence makes sense or not? Doesn't make sense. Okay, so what am I doing here? So I got this tube, right? Every tube, I got it. Yeah, I got every tube. And from every tube, what do? I found the finite subcover. But for every tube, I trim it. I trim the UI up to UN such that they become a, how to say, uniform. Trim it so that I just need one UX to cover the whole vertical line. Previously, you need U1 up to UN different one. But now I unified it. I just use UX to control the cover for the line X cross Y, singleton X cross Y. Then what do I do now? Like what you say, I consider every X, every X I can do this cube thingy, right? And then I consider the UX at every X. Can you imagine what I say? At every X, Y, you build this tube, and then for all this tube, you consider the intersection of UI. And then I take the collection of this intersection. And then this collection is indexed by what? Indexed by point in X, because you are considering every point in X. Right? Does it make sense? Make sense or not? Okay, draw picture. Picture is easier to say. But even if I draw picture, don't always rely on picture. You need to build a, how to say? You need to learn a skill that when people speak to you, you can imagine what people say. Okay, let's do it. So let's say this is x1 cross y, and then this one is a s2 cross y. And then what do? You form the tube, right? You form the finite tube that the compactness of y gave you. So for each tube here, how do you form ux? So ux1 should look something like, ux1 should look something like this, us1. us1 cross all the v. Right? So this horizontal part is ux1. And then us2, you also take the intersection of all the ui first. So this is ux2. Make sense? Okay. Does it make sense? Yes, question.
But you consider the open cross.
So yeah, so the problem here is this open cover is whose open cover? This is just the open cover for X. Yeah, we don't need to consider everything first. We just consider X because now we want to argue why across horizontal we also have finitely many. That's our point. Vertical we already know already. Vertical we already know there's finitely many. VI is finitely many already. Now we just need to consider why the horizontal is also finite. Okay, so this is the open cover of X actually. Okay, make sense? So now I think the story should be easy already, right? Because you have an open cover for X. Since X is compact, then there exists a finite subcover. How do you label this finite subcover? Actually, you can label by point in X. But how many points you need? Finitely many points. Finitely many points. Okay or not? Does it make sense? So I cover the vertical one with finitely many, and then I also cover the horizontal one by finitely many. Make sense? Okay. Okay, so let's see, go back to your example. Okay, we do this one. Let's say we don't trim it. We don't trim it. We don't trim it. So if we don't trim it, then what do? You also consider all the X. I don't know. For all X. So how should we label this guy? So, I mean, I think we should label it like, let's see, how should we do this? So, so you know what your picture looks like? So your picture looks like this. So, line here, line here. So we didn't trim it. So we didn't trim it. So we just take a bunch of open set like that. Okay, we didn't trim it. Okay, we didn't trim it. So we just take all of them. So how do we argue? Across the horizontal component, we have finite limit. Potentially, this VI is different. So, I mean, let us be a bit more careful. So here is V. So let me put here. So let's say here is U1, comma. So don't put comma. So this put here. U1, X1 cross. Let's say this point is X1, and then this point is X2 cross V 1, X2 like that. Okay. And then the other one is here is X1. And then here is a U of 1, X1 cross V of 1, X1, X2, like this. Okay. So potentially, this U and V, they could be all different. They could be all different. Correct or not? Could be all different. So, so what do you do here? You also union all the X, right? So you take the union of all X in X of UX cross VX. This guy is a cover of X cross Y. Like that. So the advantage that I did just now is I pushed the question to compactness of X. But this problem here still live in X cross Y. Is there a way to introduce compactness of X on? Is there a way? Is there a way to do it or not? I didn't say cannot. I just want to ask you, is there a way to do it? Or X is compact, so UX could be finite. Okay. So, I mean, okay. So first of all, you need to argue first, UX is a cover of X, right? So, okay. So let's see. So do we have this kind of result or not? Let's say, do we have this kind of result? Yeah, this kind of result. I think Sayed got do some similar question to this kind of thing, right? Are you familiar with that? Not false. This statement is false. Yeah, your counter example. I don't know. This one I don't know. Not sure. Yeah. So the problem here is how you introduce the compactness of X. Zixian says straight away introduce here. So how do you introduce to UX here? For what we know now, is this union, the whole union of this product set is a cover of X cross Y. That's all. That's all. So you need to have a sentence to tell you that maybe union of UX is a cover of X. How to deduce that? Okay. You get what I said? You get what I said? Yeah. So from this sentence alone, how do you deduce that? The union of UX is a cover of X. I mean, it is, right? Because for every point it's in X, it lives in some UX, because this is how we build the UX. I don't know. Oh, actually, it's different. We didn't build our UX like that. We just simply call this U cross X UX and VX. Actually, more precisely, actually, we should do like this, because we only, how to say, we only know about what is, we only take the union of UI cross VI such that it covers the line X cross Y. That's all. Okay, we didn't know about UX and VX actually. I mean, we never defined that. What is UX and VX? Okay, because my UX is different. My UX is the intersection of UI. But the idea just now was you consider the union of your tube like this. Okay, so this is just a union of product of open set. Okay, that's all we know. Okay, so that's all we know. So how do you push this union so that you can use compactness of X? This is the problem. If you want to use this construction, I didn't say cannot, but you need to solve it. Any idea, no? At least for now. To think about this idea, right? You need to think about the actual case, you know. You need to think about this actual case here, right? You need to think about actual case. So let's say you really don't want to trim your open set, right? You don't want to trim your open set. What happens? They will like keep overlapping each other. Right? I mean, it overlap in an irregular way. Right? So overlap in an irregular way, like that, maybe. Okay. So in that case, how do you control the horizontal component? Or how do you introduce the control of the horizontal component into your union of UI? At least from this picture, how do you control? From this picture here, how do you control? From this picture here, how do you control? So from my construction just now, right, should tell you that the height of this open set shouldn't be a problem. It's just the UI. But your problem is you mix different UI together. Okay. But when you mix UI together, if you forget the height, your UI is the longest UI. You get what I mean? Not longest, I mean, is the UI that contains all the, is the U that contains, I mean, okay, the U part of this U cross V, the U part of this U cross V is, the U part of this U cross V contain all the UI. Does it make sense or not? Does it make sense what I'm saying? I think it doesn't make sense. Because why? If you take union of this guy, right, it's not a product of set even. Most probably not. Correct or not? Because you like overlap differently. It's not a product. It's not a product set. So it's really hard to control it. Really hard to control. You can try and think about it, but I want to say these are the obstacles if we're gonna use this argument here. So the very clever thing in the proof just now, actually they call it a tube lemma. Instead of considering the union, they first intercept their UI first. So they trim the UI. Okay. Does it make sense? So that's why they call it a cube lemma. Who knows you can solve it using this method? Most probably they met this problem. So that's why they take the intersection. So they don't want to deal with this extra bit that come off. Okay. Maybe you have new method. I'm open to it actually. I would say cube lemma is the only way to solve it though. Okay, if you have better solution, then good. If not, then you need to realize what is the technical difficulty if you want to do this. At least you need to realize that. Okay, otherwise it's just boring. Does it make sense? Okay. So you really need to try make your hand dirty. You really need to make your hand dirty. Maths is like that. You need to make your hand dirty. You cannot just listen and calculate. That one is not maths. That one is calculator. So we need to discuss, make mistake, and then learn from mistake. Okay. This is how I learn maths actually. If I don't make mistake, I don't know what's the thing that governs the principle. Once I make mistake, oh, this thing is very important. So this is the principle. Can you understand what I say? Okay, can you understand what I say? So you say, so when I discuss this, right? So you need to go through this difficulty and then this technical problem. So how they go through the technical problem, they use the tube lemma we did just now, which is the taking the intersection of UI things. Okay, yeah. Then this will settle the problem that you might miss. You might cover different part of your space. Okay, make it uniform. Okay, any question? Any question? No question or no? So do you know how to think about problems now? You need to try and draw it out and then work, like see the real picture. Okay, you cannot just think. No use one, you just think. Because you don't know what's the hands-on, what's the object you are playing with. Okay, you need to try and draw. I mean, my view on maths, you should be able to visualize what you are calculating. Okay. Algebra and geometry is not too far away. Any question? This proof is quite interesting, and we will prove it for the infinite product later in the course. Yeah. For now, we don't have enough tool yet. Yes. Any question before we take a break? Any question? Oh, okay. So let's take a break first. So maybe shorter break. Let's break until 12:15. We resume. GJ and Jianxia, you guys haven't seen your midterm, right? So I will take a photo for you and then send it to you, and then you check your solution with my solution. And then if I miss anything, you can claim up. Yeah. We discussed the exam yesterday. 没有。
有办法的，就
哦，对啊，我想那一些东西。
啊，我在想这个有办法吗？我没有想过。啊？什么？不知道这个出什么问题？就问题你是怎样用那个 compactness 啊？
有
你怎样用 compactness？你怎样用 compactness？
你知道他是诶，其实他应该想这是，反正你超位，可是你反正是口吻给你啊，
也
就开始那种录啊。
我那也是
有系统啊，没有上去啊？
如果我有一个 set 还是在这边的话，
什么意思？什么意思？
如果有一个就在外面有一个多余的 set，有一个没有用的 set，就
哦，可以丢掉它，
就丢掉它这个。
啊，可以丢掉。对对对，
所以我们这边我这边考虑的是
可以用到
要有动态拍摄。
耶，对对对，那个是比较 technical 的法呀。啊，对对对对对，不要说，不然那个 intersection 会是零啊。耶，对对对，那个是比较 technical 的法，对。
那你的疑问是不懂那个 U 想去帮，因为你要讲它是有哪个思考哦，那你不懂你要去判断哪个 U 的感觉，
对啊，
是不是？
对啊。
可能到时候他们也是
比如说啊，你选了这个 U 过后，不是你下一个 U 要选谁？
所以你下一个要选的 U，讲不出一个，所以他们打 intersection 哦，那边是因为每一个都会有在里面，所以他们才会有。比较那个，我是在想，比较那个几个还是在想，对，
要怎样选那个 U？如果
因为我是讲过一个的，
啊，
有，我是想不到，
呀，要选哪一个 U？那有 N 个 U，然后你要选哪一个 U？
到最后你是什么的设计是他们的什么的，然后你就讲他是团队的那个什么，然后就
那又是回去刚才啊，
之后又是回去，
假设不要用最小那个呢，用任意一个哦，
可是第一个你就怕有电，不是？
直的时候会有 gap，就是放回去的时候，
对对对，我就是怕会有电嘛。
只要放回去的时候怕会有问题，所以随便选一个先咯，先做做看。如果选了一个的话，let's say 随便选一个，这个随便选一个的话，哦，另外一个可能也随便选，反正 cover 得了不是？随便选，全部随便选吧。
可是你随便选的话，你就几乎选到会有电的咯。
gap 是发生在 vertical 里面，横的应该是没有 gap
我们就是有电，
啊，横的会没有 gap，但是是等你放回一直的时候会可能会出现，懂什么意思吗？
可是如果你用 cross union 比的话，
哪里？
你就变成整个桶是就是这样子吃啊。然后还是你要讲那个这整个会有机会不是它的小泡沫，
啊，对，那个
是不是？你要讲这个是
这个是啊，对，这是大的地方的。
那它是一个 larger set，你不知道你的那个有什么。
所以假设我随便选了过后， as is a finite UI, and then finite UI 过后，我再拿回去 cross 回之前的 VI，所以我要 cross 谁的 VI 也很重要哦，因为我这整圈里面，这整圈 UI 里面有很多 x 在里面，每一个 x
对，你不是讲 cross BI 的，
没有那些我们找到 finite linear 嘛，对不对？
对，
OK，随便 pick 那些随便 pick 很 random，随便 fix 一些 UI。OK，and then 我找到 finite linear，假设这四条线咯 finite linear。哎，你想一下来，这四条线里面啊，有很多点在里面，很多点里面本身有自己的 tube 啊，本身有自己的那个
哦，
vertical
对
band，然后所以你要选谁的 VI。
也会考，也会回到一样问题
还是，所以你是说这个 UI cross with union VI？
是哦，
对，我想一下啊，也 make sense 哎，想一下
这是反正是
，UI cross with
外面你要紧
union on VI。
是哦，只要 contain 完全部里面的就好了，你 contain 不 contain 其他东西不要紧，那是可以的。就你我那时候
所以你随便选一个点也是啊 arbitrary point within UI 啊？对，你是说没有？现在问题是我这边很多点嘛，我随便选一个点，是不是？我随便选一个点，and then 我就拿它那条线 homeomorphic 的那些 BI，感觉可以，感觉可以，我想想，
那什么
感觉可以。
出来挺
说，这些是 U1、U2、3，finally many U，and then U1 cross union of VI X such that X 是在 U。OK，let's say 这个是 J 啦，UJ 里面，so such that J 是在1到 M 里面，and then union of 这个是 UJ
就是
cross with union of I 等于1到 M，好像可以耶。啊，然后你在 union 这整个东西是 union J over 1到 M。行，这个会啊，没有，刚刚好，刚才用这个比，说 X cross Y 会在这个里面，感觉可以耶，感觉可以耶。哦，看不到哈，OK，换一下颜色，诶，感觉可以耶，感觉可以啊，哎，没有。Hello, testing. Okay, well, we like tutorial. I think somehow we work out. I mean, this is the finite subcover that we trying to propose here. So what's this finite subcover here? So what we do here is for each x, right? We build this band here, correct or not? Homeomorphic band. Not homeomorphic band, but the compactness that give you this band here for each vertical line. And what we do is we pick a random UI for each point. Okay, we pick a random UI from each point. And then our claim is union of these UI X, right, should cover X. Makes sense, right? Because every X should belong to some UI. So if we pick UI X, union of any of them should contain X. So from here, we can use compactness of X to reduce this UI X. Okay, so for example, we reduce it to 4 of them here, 1, 2, 3, 4, for example. So the now problem here is how we rebuild the whole finite subcover. Okay, and so just now, Wenchuan suggests that you just pick any point inside this UI. Any one point. Picks one point. Okay. And then what do? You also look at this X cross Y line. And then you will get a bunch of VI, right? Finite VI. What do? You union all the VI. Okay. You union all the VI. And then you take the union of the VI cross with UI. Does it make sense or not? Does it make sense? Does it make sense or not? Let me ask you a question. So if I take a set cross with a union of a set, union is a bunch of set, do we get something like this? I think we do, but I think we have this kind of thing. Oh, don't know.
I feel a bit circular.
What do you mean by circular?
Because at first we define X cross Y now.
Yeah.
We try to show that X cross Y is compact first. Compact first, and then you know the Y, like what I understand is Y is having a finite subcover, and then
yes.
thing like that, and then
let's call it a band, open band. Yeah, okay, let's call it open band.
Then X, by compactness of X, you also get this, and then you feel like you just go back to the thing you want to do.
No, I mean the problem with that statement is we haven't settled the horizontal component. But now we settle the horizontal component, then we need to show it is finite cover for the whole product space.
But we construct something like that.
No, I mean we need to produce a finite subcover for our product space. But we only settle the vertical and horizontal just now. So how to put these two things together? Make sense? Okay. So just now what we suggest here is you just simply pick any point in this finitely many UI and then consider the VI, all the VI in the band for the X cross Y. And then you take union of this guy. And then this should be just a finite union of what? Of your open set. Can follow what we say? Can follow no? Can follow? If we write into this form, right, I think this one is easier way to see it, right? Like literally, you are taking M cross N thing. Yeah. What do you think? Okay. Only you, okay? Make sense or not? Does it make sense to everyone? Does it make sense or not? Make sense or not? Does it make sense? Yeah.
Yes.
Yeah. Yeah.
Was it choosing the UX?
Uh-huh. Yeah. Okay. Okay. I mean, try and write it out. Try and write it out formally. I think it works. Yeah, I think it works. And then I think it can be written better using this equality here. I think this equality should work. Yeah. I think this equality should work. And then if you have this equality here, and then this set will be looks better. Actually, it's a union of two index set. So also matches out how we understand product set, actually. Okay. So you sum across N and then you sum across M. Okay. Yeah. I think it works as well. Can or not? Can understand? Does it make sense? Okay. Yeah. All right. So let's continue. Let's continue. Let's continue. So a subset of a metric space is bounded if there exists a real number M. I think this M should be positive. Okay, such that distance between A and B is less than for all A, B, A. Okay. So easy proposition is if every point is bounded by a value M, then you can say that you can see that actually a subset of a metric space is bounded if and only if for any point in X there exists a finite radius N. So finite radius N also positive, such that A is in the ball of X, comma. Or in our notation, I think we write like this. Okay. So to prove this, you just use the triangle inequality. Okay. Can you imagine this statement? So every 2 points, right, is bounded by some values. So you are trying to bound every point around you using this number. Okay. Okay, so we will skip this proof. This is almost using a triangle inequality. But what we're gonna do with this boundedness is, I think you have seen this before. That is in Rn with the Euclidean topology. A is compact if and only if it is closed and bounded. Okay. So if it is closed and bounded. So in particular, right, Rn itself is not compact because it's not bounded. Okay, actually the Rn is not bounded, not compact. But to find a compact subset, you just need to make sure that your set is closed and bounded. Okay, so which direction should we prove first? Do you think which direction you want? Which one you think is easier? Usually this if and only if direction, right? One direction is easier. Okay, which direction is easier? Do you think? Which direction is easier? Complex implies closed and bounded. So let's try that direction first. So in this direction, you need to suppose that A is compact, and then you need to show that it is closed and bounded. So you want to show it closed first or bounded first? Say, why is it closed? Why is it closed? A is already compact. What do we know about compactness and closeness? Do you remember? When is a compact set closed? And when's a compact set closed? When's a complex set closed? Huh? Yeah. So what's the statement for it? What's the statement for that? Compact in Hausdorff is closed. This is what we proven last time. Okay. So is Rn Hausdorff or not? Yes. Okay. Since Rn is Hausdorff, A is closed. Why Rn is Hausdorff? Just play around with your epsilon ball. Okay. If you have A, B, they are different, there must be a distance between them, which is A minus B. And then form your disjoint open ball. Okay, with radius less than A minus B over 2. Yeah. Okay, so it is closed. How about bounded? Bounded. How about bounded? How about boundedness? Boundedness, somehow you need to use this proposition here. Okay, so if you want to show a set is bounded, make sure that your set is bounded by, is lying in some finite ball, finite radius ball. So how do you choose your ball? How do you choose your ball? Yes. So so which cover you want to apply to get this A contained in some finite radius ball? From the origin. So good. So we can consider a specific open cover, right? So we can start from the origin. So suppose B R A. So how should we write this? So Bn 0 such that n is an open cover of air. Is this an open cover of air or not? Quite big, right? Cover almost everything already. But since A is compact, you only need finitely many of them. This means this n could end at some point. Okay, okay. There exists an n greater than 0 such that A is in B n 0. Okay, so then it is compact. One property about this ball is it is nested. Okay, so if it is finitely many of them, you can just look at the largest one. Okay, yeah. So you need to make a clever choice of the ball. Of course, you can use different ball. You can cover every point with a ball also can. Then that one a bit troublesome. You need to have finitely many, and then you need to take care. Okay, take care of some different point will have different ball. Okay, yeah. But why is this easier? Because you relate everything to the origin. Yeah, of course you can use different choice. Then you need to argue differently. Okay, sure, good. So we have done one direction. How about the other direction? Suppose it is closed and bounded. Then you need to show that it is compact. Okay. Maybe you can straight away prove from definition. Okay, but we're gonna use the property we have. So we're gonna use the theorem that we proven before. That is closed subset of a compact space is compact, because since we already know that this set is closed. Okay, so we just need to show that it lives in some compact set, compact space. Okay, so which compact space you can find it live in? Sorry. Sure. So since A is bounded, that means what? Similarly, there exists n greater than 0 such that A is in some ball. Okay, but if there's some ball that's other than the origin, we can make an even larger ball that contain the origin, right? Can you imagine what I say? Okay, I will draw it for you. So let's say, so let's do on R2 only. Okay, example on R2. So if you are compact set, right? So compact set, maybe something like that. I don't know how it looks like, but it's bounded, right? So I can use a ball and bound it. If this ball, the origin is not at, if the center of this ball is not at the origin, I can simply make a larger ball at the origin. Make sense or not? Okay, so you simply just add the distance between the center and the origin. Okay, to make a larger ball that contains the smaller ball, and then the smaller ball will contain the compact set you have. Okay, so by doing this, where is my compact set that contains A? What compact set you know? Just now we just proved, right? Compact cross compact is compact. So what thing you can cross rectangle? So what rectangle you find? which rectangle you want to look at? Negative n to n. Okay, n times. So negative n to n, you can imagine it is like. So here is the radius n, right? So here is minus n, here is n. So the rectangle looks like this. Oh, really is a square. Okay. Does it make sense? Okay, makes sense, huh? Right. Okay. So let's say you don't want to do this. You don't want to do this, right? You don't want to do this origin at a center ball. Okay. Can you still find compact set or not? Around the small ball, can or not? Can you still find a compact set? Can, right? So you need to able to track down the square that contain this ball. Okay. Yeah. Okay. But how to find this square? There's a lot of way. You can find very specifically, or you can just make a random big one. Also can. What do I mean by make a random big one? You just consider how tall is this? I mean, how far this sorry, diameter. Okay, you can check the diameter of this ball, and then where's the, I mean, I'll say, and the distance of this ball with your origin. Okay, and then you just take the maximum height, and then the maximum width, and then you just make your compact set. Also can. So there are a lot of ways. Does it make sense? Make sense or not? Pure max is like this one. You can use different way as long as you can build me a compact subspace. Okay, but the trick in when you read the textbook, they often offer you the cleanest way. Cleanest, right? Because every time you ask me, right, hey, why your solution can be so short one, or why I write so long one? Because we provide the cleanest way. Cleanest. There's a lot of way you can do it, but we provide a cleanest way. 干净的。Yeah. 你可以写到很乱。有时候我们以前 assignment 那个 tutor 写 feedback 就是说very messy, very tedious 这样，写太多了，没有讲你错，但是就是不好读。还有更简短的方法。Yeah. So this is one of the value we uphold in pure max. 越简短越好，越干净越好。Okay. So yeah, we found the compact set, then we are done. So what's the good thing about this? Then what we would have is the extreme value theorem. So this is the corollary. Extreme value theorem. So what does extreme value theorem says? I simple. Does the extreme value theorem say? If okay, so I think here we only do it for R. So let's do it for R only first. So let's start with a compact set function from the compact set AB to R. Okay. Okay, so I think here we only do it for R. So let's do it for R only first. So let's start with a compact set function from the compact set AB to R. Okay, and then this function is continuous. Right. Then f has a maximum value and a minimum value. Okay, so what does this mean? 什么叫做 maximum value? That is what? There exists some point CD in AB such that FC is less than or equal to every fx, and then every fx is less than fd. So this x is for all x in AB. Okay, so we're gonna use topology to prove this. How do we prove this? So the closed interval is obviously closed and bounded. So that means the closed interval is compact. And moreover, this AB, right? This interval should be connected. In particular, it's path connected. Okay. So what happened? F is a continuous function. This means what? What is compact and contented? The image. Again, the image of this closed interval should be also compact and connected. Correct or not? Continuous image of a compact set and connected set. Which implies what? Again, this image is closed and bounded. Bounded means what? It is equal to some bounded interval. So some m in. Okay, it's bounded. Okay, it's a bounded interval, closed and bounded interval. But do we have points image that agree to m and m or not? Small n and big M. Why? Is it? You sure? You sure? Maximum minimum can be realized as the supremum and infimum, right? So why supremum infimum achieved here? Because it is closed. It contains all the limit points. Okay, so you have to achieve the maximum and minimum. Okay. So since f of AB is closed, it contains all its limit point. So there exists C and D in AB such that FC equals to M, FD equals to capital M. Okay, any question? Oh, any question? Did we use the connectedness? Do we need connectedness here? Do we need connectedness? Intermediate value theorem, we need connectedness. Or do we need it here? Which statement? That one is follow from the boundedness. We need to make sure it is an interval, but why do we need interval here?
Oh, yeah, anything.
I know. But I mean, what's the? I mean, even if disconnected, lah. So I mean, where is the contradiction with a maximum minimum value? No, right? Seems like we don't need connectedness. We need connectedness? I don't think so. But intermediate value theorem, you need connectedness because you want to find a point in the middle. But this one is to argue why you have maximum and minimum. I think so. Yeah. Oh, cannot equal to interval, but yeah, cannot equal to interval. But what's wrong with that? What's wrong with that? Can we have dodgy stuff happening? Yeah, of course, we use the connectedness when we, when we identify this interval here. But let's say this interval is split up. Any problem there?
Everything is covered. Yeah. So
maybe just a cleaner way to put it.
Connected should be and then equal to the thing.
But when I say equal to that thing, right, is using connectedness.
Yes.
But my problem is if I don't have connectedness and then I don't exactly identify this, but it's bounded, man.
Yeah, it's bounded.
I do not say equal, but it is just a subset of equal.
I bounded and coded and connected. Supplement, encoding supplement.
Yeah. That's what I think of. But anyway, if I have connectedness, then it's easier to talk about the equation. It has to be an interval. And then a bounded interval, then we know that it looks like something like that.
It's normally not necessarily connected.
But in this case, it's necessarily connected. In this case, yeah, because we start with a connected. Okay.
Then maybe you can make the interval AB and be a little bit say, okay, 要定是一个 interval 但是是 close and bounded 就好。
You mean union of close and bounded interval? Union, no? Maybe let's say A, B, C, D like that, no? A, B, C, D. But the problem is they want to consider continuous function. If you split A, B, C, D where B and C is different, then your function surely is discontinuous. I mean, not sure discontinuous or not, but the part you look at is a separate part. It's separate part. So if you look at separate part, meaning in mathematics it's like this. If you look at separate part, you can just reduce to look at the one individual part. Otherwise, it doesn't make sense to like look at. Of course, you have this, and then you can generalize to like. Okay, good. Yeah. So these are the questions every time you guys have to ask when you see new theorems, new definition. Then you will understand the definition. Okay. Yeah. You should ask these questions. Always yourself. Okay. I'll see you next week.